So thank you very much for um, accepting our invitation, and Professor Sergey Bobkov at University of Minnesota. And please go ahead, Professor Bobkov.
Yes, also let me thank you for the invitation. It's my pleasure to talk at your seminar. And as some time ago, Alexey Karapetyants suggested to choose this topic about Berry-Esseen type bounds in the central limit theorem in terms of the Lyapunov coefficients. Recently, there was one of my papers on this topic subject, so it's the first time I am talking about this. And let me start with setting. I consider only the one-dimensional situation of say n independent random variables with mean zero and some variances, say sigma k squared. And for the sum, I require the normalization condition that L2 norm or second moment of Sn is equal to 1, which is the sum of variances. The question is how to quantify the normal approximation for the distribution of Sn by the standard normal law or standard Gaussian measure on the real line, which holds true as soon as all sigma k's are uniformly small. And one of the typical questions is how to approximate the distribution function Fn of the sum. Using, for example, the Kolmogorov distance or L infinity distance between the corresponding distribution functions Fn and capital Phi. Capital Phi is a canonical distribution function for the standard Gaussian measure on the real line. In general, I do not assume that all xk's have equal distributions, but in many models or situations, one considers the case where xk's are multiples of some random variables xi k, which have equal distributions, or ID, which means independent, identically distributed, with mean 0 and variance 1. And so the coefficient should be 1 over square root of n. More generally, one may consider weighted, one may consider multiples of xi k, and to require that the sum of squares of the coefficient is equal to 1. So here is the typical, here is the setting which I'm going to consider. Central limit theorem. A few some well-known results. First of all, one may quantify the normal approximation with the help of Lyapunov coefficients. It's the sum of LP moments of xk. Here, sorry, I forgot the index k. The sum of the expectation of xk raised to the power p in absolute value. And usually it's a small quantity. For example, in the ID model, which I mentioned before, where all xk are multiples of xik, we obtain a quantity which decays polynomially fast with respect to the growing parameter n, the number of summons. And the power of n here is minus p minus 2 over 2. So when p is equal to 3, we obtain 1 over square root of n. More generally, here is one classical statement, which is called the Berry-Esseen inequality. And it states that the Kolmogorov distance between Fn and Phi is at most a multiple of L3, which in the ID case gives the bound, upper bound of order 1 square root of n. It's called the standard rate. And a question interesting is how one can improve this, or is it possible in some situations to get a better rate than 1 square root of n? With the help in this situation, it's not possible because it can easily be seen by Jensen's inequality that L3 is at least 1 over square root of n. And so in the non-ideal situation, the question is whether or not L3 itself can be improved in this statement. Because it can be much worse. For example, when all xk have Bernoulli distributions, take values plus minus 1, this example shows already that in general, the rate 1 over square root of n cannot be improved even under high moment assumptions because such develops unbounded. So if we will use the fourth moment or fifth moment, nevertheless, it will not help. So 1 square root of n is a rate which cannot be improved in general under further moment assumptions. Nevertheless, something can be done in the case where L3 is worse than 1 over square root of n. Another problem or questions which was intensively studied in the literature is how to weaken or how to relax the third moment condition here. And is it possible to require less than the third moment? And indeed, for this purpose, one may introduce the so-called truncated Lyapunov coefficients, defined this way. It's I will call it RP. It's the sum of the expectation of xk squared multiplied by quantity which is smaller than 1, minimum of 1, and xk raised to the power p minus 2. So R3, for example, when p is equal to 3, it's anyway is smaller than L3, does not exceed L3, and is bounded by 1. So it's a good quantity, it's well defined. And so it's better. And there is the following another interesting theorem, which has a rich, long history, which indicates that delta n is actually bounded by c times R3. And this statement is usually formulated using a little bit different but equivalent setting when Sn is a normalized sum of independent random variables say k. And more complicated quantities appear on the right-hand side in place of R3. But it's easy to reformulate, to rewrite this sum in terms of the distribution of psi k. About the history, this case was considered first by Katz and then generalized by Petrov. But there was a paper by Studiev in '65, and it turned out that he also wrote a note in '50s even. It was, as far as I remember, in a local Ukrainian journal, and probably written in Ukrainian, so it was somehow missed in the literature. There was a paper by Osipov in '60s, Feller. So some people reproved, they already discovered this inequality. And there was a paper by more or less recently by Gabdulin, Makarenko, and Shevtsova, and they mentioned that, for example, same inequality was discovered by Padets in the '80s, by Barbour and Hall in 2001, with proof based on the Stein method, by Chen and Shao in 2001. Korolov, Popov, and Drafeeva studied the problem of explicit constants in this inequality, and in particular, although it's still unknown what is the best constant, they proved the statement with rather pleasant constancy, like 2.02. And it was further improved to 0.87 later on. Good. Now, I'd like to mention one theorem due to Osipov, and it about the Lindeberg theorem. The use of the quantity R3 allows one to quantify the following Lindeberg theorem. I will use some other setting for a moment. Suppose that Sn is the sum of normalized sum of independent real variables xik with mean 0 and with some variances, and Bn Bn squared is L2 norm over variance of Sn. Introduce the distribution functions Vk of x case, and then one may introduce the following two functions of the parameter epsilon. Lambda capital N of epsilon is defined this way. It's 1 over Bn, the integral, it's truncated second moment Vk, truncated over the region where modulus of x is greater than epsilon Bn. And Ln epsilon, as far as remains, sometimes it's called Lyapunov function. It's the truncated third moment of x case, where integration of x cube is performed over the region where modulus of x does not exceed epsilon Bn, and we need to perform summation. So one theorem due to Lindeberg states the following: if lambda n of epsilon, if this function tends to 0 for any epsilon, then delta n tends to 0 without any quantification. So it gives some very general, very general conditions for the central limit theorem to hold with respect to Kolmogorov disk. It doesn't matter, it's equivalent to the weak convergence of probability measures. And Osipov proved this inequality, this upper bound for delta n, where both lambda n and Ln appear on the right-hand side. And then, of course, it implies Lindeberg theorem. Very old results, maybe one can say 60s. And only recently it was realized that in this statement the optimal value is when epsilon is equal to 1. In the paper which I mentioned before by Gabdulin, Makarenko, Shevtsova. And if epsilon is equal to 1, the sum of these two quantities defines exactly R3. So what was proved before with R3 is actually was already quantification of the Lindeberg theorem. Good. It was some remark historical. Also, I'd like to mention what is the advantage of R3 over L3. Since in general we have an elementary inequality of this type for all real numbers x. Meaning of 1 modulus x squared is bounded by x raised to the power 2 delta. Suppose that delta is fixed, some number between 0 and 1. One can bound on 3 by L with index 2 plus delta. And as a corollary, one obtains that delta n is bounded not only by L3, but with L2 plus delta. And as a result, in the IDE situation, this yields the rate of convergence with non-standard rate versa, depending on delta of order 1 over n raised to the power delta over 2. And in the paper by Osipov, he attributes this statement to Lyapunov. Although I don't know, but maybe it's the case. The question of when we have this rate of convergence, like n raised to the power minus delta 2, was also studied in 60s by Ildar Abdulovich Ibragimov, and he gave necessary and sufficient condition in terms of the underlying common distribution. Good. Now I'm going to also mention or give a remark about optimality of Berry-Esseen bounds, about L3. In some situations, this bound cannot be improved. Namely, one can describe the following model. Suppose that Sn is, again, as before, is a weighted sum of independent, identically distributed random variables psi k, which means 0 variance 1. And ik are just coefficients, and the sum of squares is equal to 1. Let's introduce the third moment, which should be common for all psi k. Alpha 3 is just expectation of psi 1 raised to the power 3. And introduced also absolute moments bp, beta p. And if alpha 3 is non-zero, and the fourth moment, beta 4, is finite, then assuming that all coefficients are non-negative, then one can show that delta n dominates L3 with some constant which depends on these parameters, alpha 3 and beta 4, for arbitrary coefficients, so uniform overall such coefficients. So in this sense, L3 is best possible. And in the other situation where, say, the third moments are equal to 0, even not necessary to assume this. Suppose that beta 4 is not equal to this fourth moment of the standard normal law, which is equal to 3. And the fifth moment is finite. Then one can give another elementary law bound in terms of L4, where C prime depends on beta 4 and beta 5. So, and as a result, in this second scenario, delta n may vary in some interval from L4 to L3, but it can be large in some sense, because L4 in general is much smaller than L3. For example, in our situation, like before for the weighted sums, L3 can be bounded from below by the sum of the third powers of modulus of k up to beta 3. And this sum is at most maximum, is greater than or equal to maximum. And as a result, we obtain that L4 is at most L3 raised to the power 4 3. So it's when L3 is small, then L4 is much smaller, and therefore there's a big gap between these two and between two bounds. Good. Now, my purpose is to speak about the following refinements of the Berry-Esseen bound by combining several Lyapunov coefficients. And here is the main statement. I return back to the original setting of independent random variables, not necessarily identically distributed, and this means 0, and the variance of Sn is 1. And I'm going to combine L4 together with L with index 2 plus delta. And then the statement is that delta n can be bounded by this quantity, 1 over delta times L4 plus L raised to the power 1 over delta with index 2 plus delta. And this can be sharpened in the case of symmetric distributions xk. It's possible to replace L4, which in general can be big, by a much smaller quantity, namely R4. It's the fourth truncated Lyapunov coefficient. So what I'd like to here to stress, the second term here in this upper bound is non-decreasing. So it's not one has to optimize this inequality overall delta, because for small delta the first term is very big, but this is smaller. So some delta between 0 and 1 turns out to be more or less optimal in such inequality. And this I'd like to illustrate on one example. By the way, in the last situation, if delta is equal to 1, we obtain here L3. R4 is smaller than L3, so we return back to the Berry-Esseen theorem in the symmetric case. So it's some sharpening. And here is one example. I just shows almost random coefficients. Suppose that we have ID random variables, independent identically distributed, means mean 0, and for simplicity, the third moment is also equal to 0. Second moment is 1, fourth moment is finite. Very standard situation. And alpha is the parameter between 0 and 1/2, for which I define the weights in front of xi k. It's alpha's power of 1 over k. Of course, I need to modify, normalize it in order to get variance 1 for Sn, which is bn here is of order n raised to the power 1/2 minus alpha. And here, the main case is when alpha belongs to the interval from 1/3 to 1/2. And everything is easily computable here. And we obtain that L4 in this situation is indeed L3 raised to the power 4 over 3. So it's better than L3, smaller. And second term, L bis index 2 plus delta raised to the power 1 and delta is of the standard rate, 1 over square root of n. So if we apply theorem 2 in this situation, we obtain, we improve the Berry-Esseen bound. It becomes like that. Delta n is at most L4 plus 1 over square root of n, up to some absolute constant little c. And using the first theorem, for the range from 3 over 8 1/2, we can see that delta n is of the order L4. On the other hand, if alpha is between 1/4 and 1 over 3, then L3 turns out to be of the standard rate, the same as L2 plus delta 1 over delta. So second term is dominated here. This is not to illustrate how these bounds, when it can improve, when it cannot improve, but some improvement is possible. Now, theorem 2 can be further generalized if we replace the standard normal distribution function by the so-called corrected normal distribution function, or Chebyshev-Edgeworth correction. And this function phi3 turns out to be, it's a distribution function of a certain sign, in general sign, not necessarily positive measure on the real line, which has the same third moment as Sn. So that's how here the coefficients are chosen. Gamma is usually used to denote cumulants. It's a cumulant or third moment for Sn. It's gamma 3. If third moments are equal to 0, the fourth order Chebyshev-Edgeworth correction is not complicated. It has this form. In general, some Hermite or Chebyshev-Hermite polynomials should be written here when p is greater than 3 and 4. I decided it's better not to write too complicated formulas and define Edgeworth corrections for the general situations. This is just to give an idea how how to construct new functions. So the idea is that if we replace phi with the corresponding Chebyshev-Edgeworth correction, the approximation will be improved. It can be indeed improved by using smooth functionals of the distribution of n. For example, if you consider Fourier Stieltjes transform of phi n and for phi p minus 1, and then the Lyapunov coefficient LP can be used. But this is Kolmogorov distance, which is not so well behaving in comparison with smooth functionals. So it's not always possible to improve this approximation. Nevertheless, in the spirit of the previous statements, one can generalize it using LP instead of L4. And so the statement is very similar, just delta is raised to the different power minus p minus 2 divided by 2. Second term is the same. And so if we use this corrected normal distribution function, in the previous example, it's always possible to reach the standard rate if p is chosen to be sufficiently large. Namely, one needs to have, it should be greater than 1 or 1 minus 2 alpha. So this is the main idea. Use the corrected normal distribution. It's some side measure, but which has an analytic, very nice density and explicitly defined in order to better approximate Fn. Good. Now I turn to the proofs and would like to describe main steps or main ingredients, main ideas in the proof of theorem 2. It's, let me remind, it's here is the statement. We have two inequalities like that, and we want to estimate delta n with the help of the Lyapunov coefficients. Basic free analytic approach to this problem is to use a sense inequality. I formulated it for the case of the normal distribution, although one may also consider Kolmogorov distance between an arbitrary distribution function and not necessarily normal distribution function. But it needs to have a finite Lipschitz norm. So it's a particular case of Sn, another important Sn theorem. So delta n can be bounded up to some constant little c with the following integral. So with this statement, we are reduced to the study of the characteristic function of n. Fn is a characteristic function of Sn. It has product structure, is a product of the characteristic functions of the summons, and can be analytically investigated. The problem is here we need to choose an optimal value of capital T, very classical bounds, and concerning the normal approximation of Fn for the standard normal law, here is a characteristic function, and they are close to each other on a relatively large interval. So basic result that on the interval of order 1 over L3, it can be bounded not only by L3 but by a function which decays like the Gaussian function, and near zero it behaves like t raised to the cube. So this term is important in order to here settle the integration in SU near zero for this integral. So appearance of this term is important, of course, not just the Gaussian function. And Osipov improved the statement in terms of R3. This I'm not going to discuss today. It's also a very nice statement. He formulated a little bit differently and did not indicate some absolute constant. At least if modulus of t does not exceed 1 over 32 times R3, we obtain this bound. But we need such inequality for recall for larger values R3. This inequality is good in order to prove. So if we insert this inequality, if we take for capital T R3, for example, or 32, if you take for capital T 1 over 32 times R3, everything will be here convergent, and the integral will be at most R3. And then that's how we obtain the results which I mentioned before with truncated Lyapunov coefficients. And where is it? I forgot. This one, improved Berry-Esseen inequality. So if we follow this approach based on Osipov theorem, we immediately obtain this inequality. But in order to go to further sharpenings, we need to prove some analysis of Osipov theorem. By the way, other proofs of this improved Berry-Esseen bound were not based on the Fourier transforms. They used the truncation argument in the usual, the classical Berry-Esseen bounds. Now, another lemma which is needed is the normal approximation for Fn with the help of R4 on the same interval. So this is needed for theorem 2. Just R4 is a smaller quantity. So in this symmetric case, this inequality can be somewhat improved. But if you use this inequality in the sense bounds, we'll obtain not theorem 2, but still, because 1 over capital T will be of order R3, not was claimed before. Therefore, in the proof of theorem 2, we need to take larger values of capital T, but integrate, split the integration over the two intervals, one interval up to this quantity, 1 over 32 R3, and apply lemma 2. And on the remaining interval, we need just upper bound on the characteristic function, proper bound. That's where the second term, L with index 2 plus delta, appears. And now a couple of in order to prove, in order to derive reasonable upper bounds on the characteristic function Fn, so we need to use some simple expressions for characteristic function for single random variables. So suppose that x is just a random variable, this means zero invariance sigma squared. And then if you write down the Taylor expansion near 0, then the last here there is of course f of 0 is 1, expectation of 0 is 0, therefore there is no linear term, there is quadratic term due to the variance assumption. But the remainder term usually is written as a t cube times the third moment of x, which is not good. And it can be improved a little bit by using the expectation of minimum 1 and modulus of tx and x squared. And of course, it's possible due to the fact that f of t is Fourier Stieltjes transform with certain probability distribution, not just some function about which we know the first and second derivative. In the symmetric case, this expectation can be slightly decreased by using the different quantity. Here, the expectation is applied to the minimum 1 and tx squared, and this multiplied by x squared. It's a rather elementary statement, but nevertheless, it's better to isolate it and mention it. Another ingredient is the so-called Cox-Kemperman inequality, which gives an upper bound for the piece moment of the sum of two mean zero random variables with finite absolute modes over the p. So it can be bounded in terms of the LP norms of x and y with the following coefficient 2 raised to the power minus 2. Of course, if we don't care about this number, this coefficient, there is nothing to prove, just apply Jensen's inequality. But then we will obtain 2 raised to the power p minus 1. So here the point is that we subtract 2 instead of 1. And in that case, it becomes optimal, and the equality is attained for the symmetric Bernoulli distribution. It's a rather odd inequality, but and it has a rather elementary proof. It follows from the following deterministic inequality, where we estimate the piece power of the sum of two numbers using this expression. It's maybe for me there is no need to read it. It's rather lengthy, but nevertheless, if we insert in place of little x and little y, capital X and y, and perform integration or take the expectations, then we obtain the desired value using the independence of x and y and the assumption that the expectation of x and y is 0. One can say elementary proof, but nevertheless it's not so immediate. Good. Now I turn to the task which I announced before, upper bounds for characteristic functions. If you apply lemma 3, what is this lemma? Let me remind. F of t is a product of the characteristic function of x. If f is a Fn, it is the product of the characteristic function of sums of k. If you perform multiplication with the help of these identities, we obtain an upper bound for the characteristic function of Sn. It will be of this form. And we want to extend this interval to up to some other quantity, namely 1 over L with index 2 plus delta raised to the power 1 over delta. And this can be attained by choosing different coefficients in front of t squared. So if delta is between 0 and 2, we have a similar inequality, worse, but nevertheless it's a well-behaving Gaussian function. And but here t can be extended to larger values instead of S3. Of course, if delta is equal to say 1, then we return to some well-known inequality Fn of t in terms of the Lyapunov coefficient L3. So very standard. Now it's not standard, but it turns out to be a useful in the proof of theorem 2. Proof. So as I mentioned, Fn of t is a product of n characteristic functions of x case, and I use the following bound for the cosine function. Of course, it behaves like the quadratic function near zero, but we need some remainder term, and it should be a multiple of modulus of x raised to the power 2 delta, and then here is the coefficient which can be chosen in front of this power. And then if you apply Cox-Kapperman inequality to the random variables xk minus yk, then here on the right-hand side we should deal with the expectation of xk minus yk raised to the power 2 delta, and applying Kapperman's inequality, the right-hand side becomes this one. We cannot use 2 raised to the power p minus 1, which would be elementary due to the Jensen inequality. P minus 2 is better. So as a result, the modulus of vk squared is bounded by this quantity. Here is the elementary inequality. 1 minus some number alpha does not exceed e to the power minus alpha. So, and on the next step, we need to perform multiplication of these quantities. And if you multiply, then we obtain exactly the Lyapunov coefficient with index L2 plus delta. Of course, there is another coefficient here, modulus of t raised to the power 2 plus delta with this coefficient, but it can be simplified. So as a result, we obtain that modulus of t does not exceed e to the power minus half. This can be replaced with 1/3 of delta on the interval from 0 to 2 in order to simplify the coefficient. So that's how we obtain lemma 6. So if we apply this lemma 6 in the Fourier bound in the sense smoothing inequality, we perform first integration up to 1 over 3, and then from 1 over 3 up to this quantity 1 over L2 with index 2 plus delta raised to the power 1 delta using just upper bound Fn of t. The Gaussian here function decays very quickly, so that's how one obtains an upper bound for the second interval in this inequality. So this is a rough description of what can be done in order to bound delta n. So this proves theorem 2, and I think I can stop on this.
Thank you very much for the very interesting talk. And now it's time for questions. If there are questions. May I ask you quickly, this inequality, the modulus to the power p, which you used in the proof of one of the lemmas, is it true for non-integer p?
Which inequality you meant?
Almost in the last part of.
You mean Cox-Kapperman?
Well, it seems like, but sorry. Here, yes, this one.
It's a real number.
Real number. No, but p.
P
Just,
is
any real number, yeah?
Yes.
Greater than 2.
Yes, when p is equal to 2, we obtain equality.
Yes, yes, of course.
So including 2, yes, I did not use it for integers p. I use it for numbers of the form 2 plus delta.
Yeah. Thank you. Other questions, please? So I think there are no questions, comments.
Good.
Thank you. These results seem to be really fundamental, which you talked about.
No. There's some refinements. It's improvement for the case where the standard rate is not suggested by the usual Berry-Esseen bound. A fundamental problem are about improvement of the standard rate. And there are many interesting questions about possible improvements, open problems.
Yeah, I see. Thank you.
It's my pleasure, and thank you for listening to me. It was rather technical, so maybe not so attractive, but
Thank you. For an interesting lecture. Okay, if there are no more questions, then thank you again.
Yes.
Thank you very much.
Thank you. Have a good day.